Right, ladies and gents, review of integral calculus techniques. So we've gone through the differential calculus. Now we're going to have a look at the opposite of differential calculus, that is integral calculus. So we're going to look at you've got a copy of the table of standard integrals within these notes. So again, that's something that you're going to need as we go through the module, and you will certainly have table of standard integrals that are needed for the examination too. So you haven't got to remember, although if you're using them quite a lot, you will tend to remember them to a certain extent, but they will be there for you in the exam, table of standard integrals. Okay, we're going to have a look at the formulae for dealing with integral calculus in terms of what do you do when you've got a function where there's two x terms added together, subtracted, and that type of thing in a similar way, but perhaps to not the same depth as we did with the differential calculus. And then so that you can integrate some expressions, some definite integrals, some indefinite integrals, and then we'll look at how you use integration to evaluate definite integrals as well. Next week we'll move that on a little bit by looking at some practical examples of where you can use integral calculus in engineering, hopefully. Okay, things like finding the area under and between curves, that type of thing. Okay, from that week onwards, so next week we'll be reviewing the uses of basic integral calculus. From then on we'll be starting the new stuff that is the main topic of this module, so moving on to the more advanced integration and differentiation techniques, as well as some other things. So, review of integral calculus techniques. The process of integration is the mathematical reverse of differentiation. There's my first spelling mistake of the week, or first typo of the week. That should read: the process of integration is the mathematical reverse of the process of differentiation. Yeah. So in differentiation, if we have a function f of x is 2x squared, then the first differential of that is 4x. So by that statement at the top, if I'd written it correctly, the integral of 4x is 2x squared. So if we differentiate a function and then integrate it, we should end up back where we started with the same function. Okay? So mathematically, it's written as this. So we use this curly sign there. I don't know what it's called, okay? But that symbol there, 4x after it, times dx on the end. What that means is the integral of 4x with respect to x, or the integral of 2t with respect to t. Okay, so that's kind of the notation, and these are indefinite integrals. They haven't got any limits. Constant of integration. So, I wish they wouldn't staple these together with two staples. From the previous page, if we have a function f of x is equal to 2x squared, then when we differentiate it, we end up with 4x. So therefore, the integral of 4x must be 2x squared. So what's the process that we have to go through to get back from 4x to 2x squared? That's what we're going to be looking at. So the process is involved in dealing with different types of functions, rather like we had a process to go the other way to differentiate. If we differentiate, something we have to deal with is constants. Okay? If we differentiate from what we looked at previous weeks, 2x squared plus 7, okay, we also end up with 4x. So if we differentiate 2x squared on its own, we end up with 4x. But if we differentiate 2x squared plus 7, we also end up with 4x. What that means is that the integral of 4x could also be 2x squared plus 7. In fact, it could be 2x squared plus any constant, positive or negative. So to allow for the possible presence of a constant, which could be equal to any number including 0, we have to have a constant of integration when we integrate and obtain an indefinite integral. So when we differentiate 4x, we need to end up with 2x squared, but we also have to add a constant of integration. That can then only be found, a constant can only be found if you've got more information about the function at certain points. You can then determine what the constant of integration is. We're not overly interested in that on this module. We are interested in having definite integrals. When we deal with definite integrals, you'll find out later, the constants of integration disappear anyway within the algebra, and so you don't have to worry about them. So, what we've got now on that page is our table of standard integrals. So that's what we're going to be using during this session to get the integrals of different functions. So we've got one for a constant, we've got one for a constant multiple of a power, we've got one for e to the ax, we've got one for 1 over x sine and cosine functions. Okay, so as we go through the session, we'll be using that table to do our integral calculus. We've also got some formulae for integral calculus. So what the first one is, if you've got a constant multiple of a function, so you've got a constant in front of it, then you can take that constant outside and just integrate the function, multiply the whole integral by that constant. So any constant in front of the x squared term, for instance, can come outside the integral, and you just integrate the function on its own. And we'll do some examples. The sum rule, all we do there, if we've got, we want the integral of two different functions added together, we just integrate each of them, also applying the constant multiplier rule to the separate ones, and the answer is the two integrals added together. And then lastly, the subtraction rule is integrate the two separate functions and subtract the second one from the first one. Okay, so that's what we're going to be using. They are our standard tools for this class. Those formulae and the table of integrals on the previous page. So, first problem of the week. We've been asked to find the integral of 5x squared with respect to x. If we look at the table of standard differentials, we're looking at the one that has the integral of ax to the power of n, and it says that the integral of ax to the power of n is equal to ax to the n plus 1 over n plus 1, and that's all got to have a constant of integration on the end of it. That's the entry in the table. So applying that to this, we can say that's 5 times the integral of x squared dx. That's applying the constant multiplier. Rule. That's what we've done there. And then we integrate x squared dx. So we've got to write that as it's equal to 5 times x to the 3, because that's 2 plus 1, over n plus 1 is 3. What have I missed off? Plus c. So it's 5/3 of x cubed plus the constant of integration. Yeah? All happy with that? If we look at that, if we write that a little bit tidier, if we differentiate that, do we end up back where we started? If we differentiate a constant, it will disappear. And what do we do if we differentiate that? Multiply by 3. Yeah. And reduce that to 2. So in those two, 3 and 3 cancel each other out. We end up with 5x squared, and the constant is gone. Yeah? So that's your check with this, because differentiation is the opposite. You're unsure whether you got it right, differentiate your answer. You should end up back where you started. Constants will disappear. If you were asked to do this in the exam, and you're going to probably be asked to do something more extensive than this, but if you're asked to do that in the exam, then you're going to get marks for getting each stage correct. Okay? For doing that, when your answer's wrong, I'm not sure about that. But it's really comfort for you that you've got the answer right. Yeah? What's the second one? 2t cubed. dt. So what's the answer to that one? What does that equal? Well, it's got to be t to the something. What we got to do? Deathly silence. What did I do up there with the index? Yeah, so increase the power by 1, divide by the new power, and we've got to multiply by constant in front. And, lastly, plus c, constant of integration. Yeah? Now, applying that, bearing in mind that the sum rule says you've got to deal with each of those in turn, let's just go back one step and put an extra one in here. What do we do? to find, what about the integral of I'll change that, that's the one on the next page, integral of 6 dx. How do we deal with that one? Do you think? Yeah, what you can, are you saying we can consider that this is the integral of 6x to the 0 dx? Yeah. Well done. Because x to the 0 is 1, that is still the same. But if you integrate a constant, x has got to come back, and it will, because we'll write that out as 6 times x to the power of 0 plus 1 over 0 plus 1. So it becomes 6x to the 1. Yeah, and x to the 1 is x, so we're back to having x return. So where you integrate a constant, you just multiply that constant by the independent variable that you're integrating with respect to. So 6x, we integrate that, become 6, the constant 6 becomes 6x, just with respect to x. So, applying what you've already been shown, have a go at doing that one, bearing in mind the sum rule. So you're going to integrate each of these 4 terms separately, and either add them together or subtract them according to the signs in that function. So have a go at that one, see if you can do that. Right guys, how are we doing? First start should be using the sum and subtraction rules to say that's all the separate integrals dealt with and added or subtracted from each other. So integral of 4 dx is yeah, anything else? Well, yeah, you can do, right? I'll talk about that in a minute. So if you'd done that on its own, that would be 4x plus c. And then we've got a plus integral of 3/7 x. Three 14ths of x squared plus its own constant. Yep. Minus 2x cubed plus c. However, that, and that are all just numbers we don't know, so you might as well write it with just the one big constant, 4x plus 3/14 x squared minus 2x cubed plus c on the end. Yep. So there only needs to be one constant of integration, because you just add them all, sum them all together anyway. Everyone agree with that? Yeah? All got that? If you differentiate it, would you end up back where you were? Here, yes, the x would disappear with that, wouldn't it? This would become 6 over 14, which is the same as 3 over 7, and that become x to the power 1, which is x, and this would become 3 times 2 is minus 6, yeah. and x to the 2, yes. Okay. Problem 3. Where's my... What would we need to do with a here? Integral of 2x cubed minus 3x all over 4x. Multiplied by 4x. Not really. You do need to get rid of the 4x on the bottom. What, divide top and bottom by 4? Will they... What you... there's another way of writing that. How could I write that as two separate fractions? Yeah. So that's a start. What could I now do? Go on, Michael. What? Yes. What you're saying is that cancels, and that goes to a 2. Yeah. Yeah. That. So what we've got now is the integral of 2x squared over 4 minus 3/4. And that actually will simplify still further, won't it? Because that's actually half x squared. Yeah? Agreed? Now you can integrate it, can't you? Yes? Well, you wouldn't be given one that you can't simplify. You also wouldn't be given one that you can't simplify with the techniques that you know and have been taught. Yeah? So I'm not going to ask you to do something that we haven't covered. Yeah? But you do need to get used to spotting what you can do, and the key to this is getting rid of the x, and that quite often is getting rid of the term in the denominator, which means kind of this multiplying out thing. Okay? Yeah? That's only that spotting what you need to do will only come with practice. Yeah? So what is the integral of, because we've got to do the integral of that bit with the integral of 3/4 subtracted from the integral of x squared over 2. So what are the integrals of those? x cubed over 6 Anyone disagree with that? Constant. The variable just returns to the constant. Add 1 to the index and divide by the new index. So our bottom line here becomes 2 times 3, 6. Yeah. Okay. Constant of integral on the end. Please, we had someone last year who, when we were doing indefinite integrals, kept forgetting the constant of integration, and then when they done definite integrals, they kept putting the constants in when they didn't need to, which don't matter in that respect because they cancel out anyway, but that's by convention, as you'll see. You just leave them out because they cancel, they always cancel. So that's that one. What about the other one? It's 1 minus t all squared. What do you reckon we can do here? What would you attempt? And sometimes it's about trying something you think might work, but it doesn't, so you try something else. We'd definitely be going to be going into those kind of realms on this module of where you're going to have to try things and see if they work. What could we do with that one? Yes, so let's go down this. What you're saying is multiply out these 1 minus t, 1 minus t, multiply that out. Yeah? Multiply out the bracket. So what is that multiplied out then? What do we have to do? Yeah, multiplying out those brackets, we have to do 1 times 1, 1 times minus t times 1, minus t times minus t. Becomes a plus t squared. So we multiply everything in one bracket with everything in the other, and we end up with that. Now can you integrate that? I believe so. Right, what we got then? Integral of t squared is going to be t something or other. T over 3, and the t is cubed, minus t squared plus t plus c. Yep. So again, that's looking for things as to ways, can we turn this into something that looks like one of the options in our table of standard integrals, so we can actually integrate it. Everybody happy with that? Yeah? Please shout if not. So what about the integral of 3 over x squared? What can we do with that? Yeah. Move index to numerator, because that you could write that as an integral of 3 times 1 over x squared, and you'd have the same thing. Yeah, so we can bring this up to the top, the integral of 3x to the minus 2. We bring it to the top and change the sign. So the integral of that will equal minus 3 over x plus c. Everyone agree with that? Anyone not see how you got to that? Do we want some stages in there to help? We're going to end up with x, and we're going to add 1 to that index. So it's going to be x to the 1. And then we're going to x to the minus 1, sorry. We're going to divide by the new index. And that 3 has got to stay in front. Yep. 3 divided by minus 1 becomes minus 3. X to the minus 1. Okay. And then we can put it back to having, because we initially changed the function, add a positive index on the bottom to one that, if you gave that answer plus c, you're right, there's nothing whatsoever wrong with that, and you get full marks. But you can also move it back to its original form of minus 3 over x to the power of 1, so bring it back down the bottom, make the index positive, and make it plus c. So that, or that, as far as I'm concerned, if you were asked to do that in examination, which you're not going to be asked to do something as easy as that, but a question might contain a little bit of that type of integration in it, then you're going to get the same mark for that answer as you're going to get for that answer. Yep. And probably credit for showing the steps in between as well, should you have got the final answer wrong but got some of the working right, and you could get some marks for that too. Okay? Right. What I want to just cover is that. Don't look at your table of integrals. Apply the rule you've been using to that. So what would we do first? Bring the x up. So we'd write that as yeah. And then we'd start to do this. We're going to have x. We're going to add 1 to the index. So that becomes 0. And we're going to divide by the new index. That's equal to 1 divided by 0. What happens if you put that in your calculator? You get an error. Yeah? So that's why in your table of standard integrals, the entry for, first of all, the entry for ax to the n says that n must not equal minus 1. Yeah? And there's a special entry for the integral of 1 over x, and that is that the integral is ln of x plus c. Okay? So, under pressure, you might end up trying to apply that in an exam because you think that's the way to go, but 1 over x is a special case. Okay? So, the integral of I, integral of 4 cos 3x with respect to x. Again, we can apply the constant multiplier rule, so that it is 4 of cos 3x dx. So immediately bring any preceding constant outside the integral sign. And then the standard integral for cosine function is that it is 1 over a minus 1 over a sine ix plus c. That's the entry in the table we're using. So we're looking at 4 times minus 1 over 3 sine 3x plus c. Everyone agree with that? Oh, hang on. Yes. Picked the wrong one. So that's not negative. That's 4 times a third. So equals 4 thirds sine 3x plus c. And you could check that by differentiation if you wanted to. So have a go at the other one, 5 sine 2 theta. Because it's a constant multiplier, isn't it? Yeah? On page 1, 2, 3, 4, 5, Mike, you've got those formula, haven't you? And if you've got a constant times a function, you just take the constant outside the integral. Yeah? Everyone agree with that? or more better, minus 5 over 2 cos 2 theta plus c. Happy? Okay, so that's finding indefinite integrals, which you need to do to be able to, you need that skill to be able to evaluate definite integrals. So, definite integrals. Guys, please. Up until now, we have integrated functions to contain indefinite integrals that include a constant of integration. But that constant of integration can only be found if you know some more things, Curtis, about that function. Some details about the value of it in certain places. Definite integrals are integrals that have some limits applied, so they can then be evaluated. For example, if we want to know the value of the integral of x squared with respect to x as x increases between 1 and 3, 1 and 3 being the limits, we write that definite integral like this. So we put the limits top and bottom, the lower limit and the upper limit, top and bottom of the symbol, and then the function afterwards. We're saying we're going to evaluate what's the evaluation of that integral between values of x between the bottom limit 1 and the top limit 3. So if we look at evaluating that integral, the first thing we have to do is integrate and place in brackets with the limits. So the integral of x squared is x cubed over 3. There. All agree with that, yeah? Add 1 to the index and divide by the new index. And we got our constant of integration. And then on the brackets we put our top and bottom limits there. Then we can evaluate. We say that that definite integral is equal to its value when the limit is 3 at the top, subtract its value when the limit is 1, the bottom limit. Okay? What we do then is evaluate this one with x equal to 3, this one with x equal to 1, plug all the numbers in the calculator and come up with an answer, this time with a number. So we put in 3 to the power 3 over 3 plus c. We put in 1 to the power 3 divided by 3 plus c. Because that's c minus c, the constants of integration disappear. And they always do when you evaluate definite integrals. So it's more normal just to leave them out in the first place, having done the integration, because you know they're going to cancel out. So the value of this bit is there, 9. The value of that bit is there, a third plus c. And we got a c minus c, so they disappear. We end up with a value of 8 2/3. So when we evaluate a definite integral, we end up with an actual answer that is a number, no variable anymore. You all kind of see that process, yeah? So let's have a go at one. definite integral of between 2 and 1 of 3x dx. So the first thing we've got to do is integrate. So the integral of 3x dx is 3 over 2 x squared and we don't need to put the constant of integration, but we do need to put our limits in. And then we write that that equals, I'm going to use square brackets, it's easier, 3 over 2 x squared, where the limit is 2, minus 3 over 2 x squared, where x is 1. And I do recommend to start with at least you write these things out. 3 over 2 times 2 squared minus 3 over 2 times 1 squared. And again, you want to be careful when you start getting negative signs in there. Use brackets liberally before you multiply everything out. So that bit is when, this bit is when x equals 2, and this bit is when x equals 1. We can then plug those into the calculator. The value of this bit, effectively 1.5 times 4, I make that 6, yeah? Minus 1.5 times 1, 1.5, or 3 over 2. Am I right? 4.5? Yeah? So have a go at the second one on that page. Integrate, find a definite integral of 4 minus x squared